Hello students, welcome to the Engineering Projects YouTube channel. I am Mariam. We have started the series of Electronic Devices and Circuit Theory by Robert L. Balestid. We are discussing about our chapter number 1 and its name is Semiconductor Diodes. Today our topic is rectification. What is rectification? The conversion of AC input signal into DC signal is called rectification. So simply the conversion of AC input signal into the DC signal is called rectification. AC signals are the positive and negative signals. It consists of positive and negative signals, but the DC signals are unidirectional signals. DC signals are unidirectional signals. So we will convert the AC input signals into the DC signals. The principle of the rectification is the current flows during forward biasing and the current does not flow during reverse biasing is the basic principle of rectifier. You know, when we connect our diode, this is our diode and it is the P side of our diode and it is the N side of our diode. When we connect the P side of our diode with the positive terminal of the battery, then it will be the forward biased and it will flow current. Why it flow current? Because P type has the holes, N type has the electrons. And when we connect to the positive terminal of the battery, all of the electrons will flow towards the positive terminal of the battery because the conventional current flow in the books. But actually the current flow because of electrons, but in books we will consider the conventional current which flow from positive to negative. So current flows during forward biasing, but current does not flow during reverse bias. Reverse biasing is the condition when P type is connected to the negative terminal of battery, N type is connected to the positive terminal of battery, and when P has the holes, N has the electrons. These electrons, here are some of the electron hole pairs in this region which are generated due to the thermal agitations. These electrons will move toward this positive terminal of battery and a very small amount of current will flow which will be approximately equal to 0. So we can say that current does not flow during reverse biasing is the basic principle of rectifier. Types of rectification. We have two types of rectification, which is number 1 is half wave rectification, number 2 is full wave rectification. Now let us discuss half wave rectification. What is half wave rectification? Half wave rectification is the input signal contains positive and negative half cycles. This is our input signal and it is the AC signal and it contains both cycles, positive half cycles and negative half cycles. But the output signal will contain either positive half cycle or negative half cycle. The output signal will contain only either positive half cycles or either negative half cycles. This is the half wave rectifier. Half wave rectifier is that rectifier which will contain only half of the circles, half of the cycles, either positive, either negative. This is, now let us discuss the circuit details. This is our diode. This is our resistance and it is connected across the output and it is our transformer. The function of diode is to pass the current or stop the current. The function of the resistance is to hurdle the current. In one pulse, it has the positive polarity here and negative polarity here. But in the other pulse, it will have the negative polarity here and positive polarity here. So transformer is basically used to generate the AC signals. So AC input signals are produced by this transformer. So what is the working of our half wave rectifier? input signal is provided to the diode. This diode is provided with the input signal by this transformer. When the positive half cycle comes, let us consider, here is the polarity positive and here is the polarity negative. When the positive half cycle comes, then this is the P side of the diode, this is the N side of the diode. P side is connected to the positive terminal of battery, then it will act as the forward biased. When it is forward biased, then maximum current can flow. It will act as the closed circuit like this. When we have the positive half cycle, then our diode will act as forward biased. We will have very low resistance. Our circuit will behave as the short circuit. We will have the maximum value of current and our voltage drop will be maximum. So in forward biasing condition, you have to note all of these steps. For forward biasing condition, here it will be the P side. P side contain hole, N side contain electrons. All of the electrons will flow in this direction and the current start to flow. The resistance, if the current, maximum current is flows, then in this case resistance will be low, and if the current is flow, it means the circuit will be the short circuit, not the open circuit, and the voltage drop will be the maximum. And for the positive half cycle, we will obtain like this diagram. So when the negative pulse obtained here, let us consider, we will have negative pulse here. In this case, P side, this is the P side and this is the N side. When there is P terminal connected to the negative of the transformer, then we have the reverse biased. We have reverse biasing. In the reverse biasing condition, no current flows because the circuit behave as the open circuit. So negative half cycle comes, then the circuit, our diode will behave as the reverse biased diode and our resistance will be very high. Our circuit will behave as the open circuit. Our current will be very low. It will be approximately equal to 0, not exactly equal to 0. It will be approximately equal to 0.2 microampere, something like it. Its value will be in microampere or nanoampere. Voltage drop will be approximately equal to 0. It will be 0.3 volt for germanium. Not equal to, exactly it will not equal to 0. All these two values are exactly 0 only for the case of ideal diode. But we have the practical diodes, so these two values will not be exactly 0. So for negative half cycle, we will have reverse biasing, high resistance, open circuit, low, very low value of current and very low value of voltage drop. Pulses made smooth by filters. I have discussed here that conversion of AC input signal into the DC signal, and the DC signal is in the form of straight line, not in the form of pulses. So these pulses are made smooth by using filters. How these pulses made smooth? Like by having filters, our pulse will be like this. So our pulse will made smooth by using filter. Which filter we can use? We can use the capacitor filter here to make our pulses smooth, to make our signal DC signal. Number 5 is negative half output cycles obtained when diode is inverted. Suppose like when diode direction is P here and N here, then we have the such kind of diagram. And for positive half cycle and for negative half cycle, we will have no circles. We will have no cycles. Like over for negative half cycle, our output voltage will be 0 at this condition. Our output voltage will be 0, and for positive half cycle we will obtain positive pulses. When we invert the direction of the diode, then we will get negative pulses. Like we have to make our diode like, we have to connect our diode like this. Then in this situation we will get the negative pulses and a straight voltage line for other half cycle. I will discuss it in detail. So student, if you like our videos, then kindly subscribe our channel. Now this is the side for rectifier for positive half cycle, and this is the rectifier for negative half cycle. Now this is the transformer, this is diode, and this is resistance. Transformer can be shown as, and now let us draw its circuit diagram. And circuit diagram for diode, it is the circuit diagram for the practical diode, and for the practical diode we have this VB is the potential barrier and RD is the resistance of diode, and here the polarity is positive and here is negative. Now we apply the equation, then we came to know that the input voltage is equal to the output voltage. So input voltage here is VI, and here the voltage will be, this is plus side and this is negative terminal of the VI, and VB is plus and here is minus. So we will write it as VB, and for RD V is equal to IR. So we will multiply here I, so we will have VB plus IRD, and for here we will have IR. We are taking output across the resistance. Now move all of these three terms towards the right side of equation. Vi minus Vb, I is taken common from these two terms. I Rd plus R bracket Rd plus R bracket close is equal to 0. Now I is equal to Vi minus Vb. This term will goes toward the opposite side of equal, and Vi minus Vb, and Rd plus R, we have a step like this. Vi minus Vb is equal to I Rd plus R. So Vi minus Vb, Rd plus R is multiplied with I. This will be divided onto the other side of equation. So our output voltage is equal to IR. We will multiply this value of I with R resistance, and now we can write this equation as R Rd plus R Vi. This R is multiplied by this Vi and Vb. So this is R by Vi, Rd plus R minus R by Vb, Rd plus R. We have make its fractions. We have write our equation into its fractions. So now this Rd, the internal resistance of the diode, is very smaller than this external resistance. So Rd is less than R, so we can neglect this Rd. R by R cancel out each other, and this equation will become equal to, this term will be equal to 1, this term will be equal to 1. So we will have V naught is equal to Vi minus Vb. So let us consider our Vi is equal to 220 volt, and barrier potential for the silicon is 0.7 volt. So we will subtract 0.7 volt from 220 volt, and we will get 219.3 volt. So this is very large value of voltage. So we will get maximum voltage, and this voltage will be only in single direction. This voltage will be in single direction, either positive, either negative. Now for negative half cycle, our diode, this is our P side, and P side is connected to the positive terminal of the transformer. P side is connected to the positive terminal of transformer, and when the negative half cycle come, then P side is connected to the negative terminal of transformer. Then we have negative here, positive here, negative here and positive here. And in this case, when P is connected to the negative terminal of transformer, our circuit will act as the open circuit. No current can flow through the circuit, and in this case we can write equation as, here the voltage will be equal to PIV, peak inverse voltage. This voltage will be gained when we have the maximum value of applied input voltage. When we have the maximum value of applied input voltage before entering into the Zener diode region. We will discuss the Zener diode into our next lecture series. Then we have PIV, peak inverse voltage at this point, and V naught at this point. By applying KVL equation, we have Vi is equal to input voltage is equal to the all of output voltages. So PIV and V naught. And in this case, we will get voltage drop is equal to 0. When no current flows, voltage drop will be 0. And Vi will be equal to PIV, and Vi will be equal to Vm, maximum voltage. Then we have PIV, peak inverse voltage. When we apply maximum input voltage, then we will get peak inverse voltage. So this is the diagram. This is the AC input signal. This is the AC input signal applied. And for the, this is the VB. VB is the barrier potential. This dotted line shows the barrier potential. And for the practical diode, we will get the half cycles like this, this and this. And this is equal to Vi minus VB. And but for the ideal diode, we will get the full half cycles. So this is all for the half wave rectifier. Now in the next lecture, we will discuss the full wave bridge rectifier. So if you like our video, kindly like, share and subscribe our videos, and subscribe our channel. Thank you.